In this module, we shall now study or learn about the points that one should be taken care of while considering glass as a physical evidence, the direction of impact cone, that is from which direction actually stone has been thrown, and other things. Now, types of fractures in detail, which is based on the impact. Now, basically what till now we have studied is that glass is one of the major evidentiary materials in many criminal investigations. The information gathered from the glass, for example, its physical properties, the direction of impact, they serve as physical evidence which actually depends on the sample available, how the glass has been broken, and the care with which the glass samples have actually been gathered, because those glass samples, they may be microscopic or maybe large. Now, most of the information actually depends on how the glass has been broken and the fractures formed. Glass type determinations compares nothing but a known sample to a glass fragment to see if the two samples match or not, that is, whether the two samples are from the same source or not. Now, glass can be actually made from a variety of different materials that differ from batch to batch. The presence of different materials in the glass makes it actually easier to distinguish one sample of a glass from another. Also, the properties of the glass can vary depending on the temperature the glass is exposed to during its manufacturing. Basic properties such as the color of the glass, the thickness, and the curvature can also help to identify different samples of glass just by looking at them. Optical properties such as the refractive index are defined by various manufacturing methods. Refractive index is the manner actually in which the light passes through the glass. This can be measured easily even on very small fragments of glass. These properties help to indicate whether the two samples of the glass are from the same source or not. Sequence of force determination, that is, an examiner can actually establish the sequence of shots by considering the radial fractures termination points. The first shot's radial fractures will extend completely, while the subsequent shots radial fractures will either be stopped or cut off as they come into contact with prior fractures. Glass analysis can be helpful in various ways. The glass fragments at a crime scene should always be collected and analyzed very carefully, because several clues can be gathered about the events that have occurred during the crime. Fragments of glass from the headlight at a hit and run scene can leave clues about the unknown vehicle. Also, the glass fragments can help police determine which direction the first bullet was fired through the glass. These clues can be gathered through the analysis of even the smallest fragments of glass. Often we have seen that it is difficult to determine just from the size and the shape of a hole in a glass whether it was made by a bullet or by some other projectile, that is a stone or a pebble. For instance, a small stone thrown at comparatively very high speed against a pane of glass will often produce a small hole which is very similar to that produced by a bullet. On the other hand, if you have a very large stone, then that can completely break a pane of glass in a manner closely resembling the result of a close range shot. However, in the latter instance, the presence of gunpowder deposits on the shattered fragments does point to damage which is actually caused by a firearm. When it penetrates a glass, a high velocity projectile, such as a bullet, often leaves a round crater shaped hole that is surrounded by a nearly symmetrical pattern of radial as well as concentric cracks. The hole is inevitably wider at the exit site, and hence its examination is actually an important factor in determining the direction of impact. However, as the velocity of the penetrating projectile decreases, the irregularity of the shape of the hole and of its surrounding cracks increases, so that at some point the whole shape will provide no assistance for determining the direction of impact. At this time, information derived from an examination of the radial and concentric fracture lines may provide a useful alternative for determining the direction of impact. When a force pushes on one side of a pane of glass, the elasticity of the glass permits it to bend in the direction of the force applied. Once the elastic limit is exceeded, the glass begins to crack. As the first fractures form on the surface, opposite to that of the penetrating force, and these fractures then develop into radial lines. The continued motion of the force places tension on the front surface of the glass, resulting in the formation of what we call as concentric cracks. An examination of the edges of the radial and concentric cracks frequently reveal stress markings whose shape can be related to the side on which the window first cracked.
Glass as a physical evidence. Glass is one of the more important types of physical evidence that is commonly overlooked. Glass is frequently encountered in burglaries and hit-and-run cases, and glass fragments may be found adhering to garments, shoe soles, or other property belonging to the suspects. Glass evidence cannot be individualized to a single source. However, there are some instances where two fragments can be physically matched together and a common origin can be conclusively established. Considering glass as a physical evidence, and if suitable samples are available, then first the glass pieces are assembled, which can actually help the scientists to know whether the fragments are from then one glass, which can further reveal the brand or pattern of the original object. Glass examinations may also reveal the following: whether or not evidence glass is similar to glass from a known source, the type of glass, example, tempered glass, container glass, etc., the direction of force, from inside or outside, used to break a window, the order of shots fired into a window or windshield. Consider that large glass pieces may have latent fingerprints present, and the broken edges of glass may have other trace evidences present, such as blood, hair, or snagged fibers. After this, the scientists look for the following physical appearances on the glass: the type of force which caused the fracture, the origin of fracture, the direction of force causing the fracture, order of occurrence of multiple fractures, whether the particular fragment has come from a particular kind of broken glass object, for example, window, bottle, headlight. Whether a fragment has come from a particular place or a particular object. Determination of direction of impact cone and glass fractures. Direction of impact cone. The patterns on the glass fractures can actually reveal the direction of the projectile. The pattern can actually reveal whether the object that caused the fracture was moving at a low pace like a rock or a fast moving bullet, whether it is a thermal stress or impact. This can really be critically important in reconstructing the crime scene. For example, if a bullet strikes a window and penetrates it, while not completely shattering it, it may have leave a hole with surrounding fractures or may not. On the side of impact, the bullet will create a clean hole, while on the opposite, a cone-shaped corner of glass is forced out. Thus, visual inspection can reveal the direction of impact. Glass fractures. Depending on whether the fracture is caused by a high velocity projectile or a low velocity projectile, there are different kinds of fractures. Radial fractures. Radial fractures will always travel along the path of least resistance, and they will always end if they encounter an existing fracture line. This fact allows an investigator to determine the order of multiple impacts to a single pane of glass. To be precise, this may occur in both the cases, that is, low or high velocity projectile. Concentric factors. These also we have studied in detail in the last module. Broken edges. When there is a cut in the surface placed under tension, the glass may not break squarely across. When a piece of glass is broken by bending from a larger piece, the sharp edge remaining on the larger piece will probably be there on the side to which the force was applied. Hudson fracture or cone. Usually, the glass breaks by tension and not by compression. For example, when one pushes window glass, it begins to break from the backside and not from the force has been applied. It breaks under tension as tensile strength of glass is always less than the compressive strength. As far as failure of tension is concerned, it is not the only mode for breaking a glass. If this would have been the case, the glass would then be impossible to break, as it would be unable to bend and create tensile stress. There is a second mechanism by means of which the glass may be broken is by the formation of Hertzian cone or fracture. A Hertzian cone is a cone of force that propagates through a brittle, amorphous, or crystalline solid from a point of contact like a bullet through glass. This occurs usually during very high energy impact. In such cases of high speed and high energy impact, a compressive stress wave will pass through the glass from the point of impact to the opposite side. Such situation is also referred to as dynamic loading. When a projectile strikes a glass pane, longitudinal compression waves are generated, beginning at the point of impact and then moving outwards in a series of spherical wave fronts which travel with the speed of sound in glass. The wave travels almost 20 times the speed of the bullet fired. When the stress wave arrives at the opposite side of glass, it is reflected and then becomes a tension wave. Upon striking the impact side, it will be reflected again as a compression wave and again launched towards the opposite side. This interactive process results in the interference of tension waves if they are coincidentally in phase. The amplitude of the waves will be additive and as a result due to the accumulation of tensile strength results in the failure of glass. Thus, a flake of glass is ejected from the opposite side. The largest flakes are at the edge boundary, while successive flakes that are close to the point of application are smaller. Glass that has been broken in this fashion results in crater, opening away from the direction of origin of space. The direction of crater depends on the speed of propagation of projectile. In case of low velocity projectiles such as pebbles, a crater may be formed on the opposite side of the glass but with no hole or a very small hole, even though the projectile does not pass through the glass. If a projectile approaches in a perpendicular fashion, crater is symmetrical. In case of a high velocity projectile, such as a rifle bullet, will yield a small hole with minimum flaking around circumference. A slow moving bullet, however, delivers more irregular hole with substantially more flaking. If an intermediate target has reduced the velocity of the projectile to even below 200 fps, the glass may show evidence of tension propagated fracture with no crater formation. Fractures in container glasses. There is a single location at which the fracture begins, which we call as fracture origin. Very rarely, the fracture will traverse the thickness of the glass wall to the opposite surface as well as being propagated away from fracture origin. The fracture in the containers arises due to the following stress conditions. Internal pressure. If a glass container fails due to excessive internal pressure, the typical fracture appearance is a straight, vertical split in the sidewall of the container, which results maybe due to the excessive carbon dioxide in beverages, from thermal expansion of liquids due to heat, or generation of gas due to decomposition of contents. It usually originates at the heel or bottom where stresses are greater. These rarely originate in the neck of the bottle, as the neck is stronger than the sidewall option. After the initial fracture, it often forks at both ends, producing a series of fractures that are symmetrical about the initial longitudinal fracture, that is, like a fan-shaped pattern. As the fan-shaped pattern diverges, it travels through the circumference and separates the neck and base from the rest of the portion. Thermal fracture. If very hot liquids are poured in cold glass or very cold liquid is poured into hot glass, a thermal shock is produced leading to fractures. These occur in the bottom of the container around circumference with no or very rare surface markings, resulting in fracture along the long axis of the container. Impact fractures. These generate the most complex stresses of any type of fracture. There are three distinct phases of impact fracture: contact stress, flexure stress, and hinge stress. Although the actual physical appearance of the fracture will be determined by the one which is dominant. Contact stresses. They are generated at or very close to the point of application of the impact force, resulting in Hertzian fracture, or results in trips along the mouth of the container. Flexure and hinge stresses. They arise from localized defect on the inside of the glass. A very slight impact would be enough to cause the container to fail. This will result in a star-like appearance on the inside of the container, while at the same time causing the bending of glass wave to the outside. The stress created by this outward bending is the hinge stress. Hinge stress fractures generally occur at the same height as the initial flexure fracture at about 45 degrees.
Let us now summarize what we have studied in this module. We have actually seen in the last modules as well as this module that glass is actually serving as a very common evidence in many investigations. Glass can be made from a variety of materials that differ from batch to batch, and the presence of different materials in the glass actually makes it easier to distinguish between different samples of the glass. The glass analysis can be helpful in various ways. Glass fragments at a crime scene should always be collected and analyzed very carefully, because several clues can be gathered about the events that have actually occurred during the crime. Glass evidence cannot be individualized to a single source. However, there are some instances where two fragments can be physically matched together and a common origin can be conclusively established. The physical appearance of the broken glass can actually tell the direction from where the gunshot is coming. At what speed is it coming? With what force? How it leads to fractures, and under what circumstances different types of fractures have been formed, both in flat glass and glass containers.